Hello everyone, welcome to what will be pre-lecture number 31. This will be our introduction to our last unit, which is about chemical kinetics. And so let's just start with a very basic definition here. What are kinetics? The field, in chemistry, kinetics refers to largely how fast a reaction will proceed from its reactants to its products. By understanding how quickly that sort of transformation happens, we can also understand different aspects about the chemical reaction. So we have something called a reaction mechanism, which are essentially the different elementary steps that make up a chemical transformation, and also think about how molecules collide with each other in order to, again, go from reactants to products. And in general chemistry, we will, of course, define these processes using mathematical expressions that we're going to call rate laws. And we are going to get into those next week for the most part, but just kind of get our basic understanding of rates of chemical reactions down in class today. Okay? So the rate of a reaction, if we generally defined it, is the change in the amount of reactant or product per unit of time. And so these are basically generally measured on time dependence, and we are measuring time. We are going to also be measuring concentration of our reactants or products then. And so, for example, say we have a reaction that is hydrogen peroxide, this H2O2, and it decomposes to water and O2 gas. And so if we wanted to understand the rate of that reaction, we could say on the most foundational level that the rate of hydrogen peroxide decomposition is going to be equal to the change in concentration of reactant over the time interval. I will point out here this negative sign, and of course, hopefully if we think about it, it makes sense why this would be negative. It's because we're decreasing the concentration of H2O2, right? So we will have a negative change in the concentration of our reactant, and we will have a positive change in concentration of products. And so if we were to write that out in even more mathematical terms, we could say that if we measure the concentration of H2O2 at some point, or 2 points, I should say, and we mark down the time at those 2 points, we can essentially just do what is the most basic step in algebra of one concentration at one point minus concentration at another point over change in time, the change in time being time at one point minus time at another, and we get our good friend delta here. So delta concentration of H2O2 over change in time, right? And so if we were to look at this, this is from the textbook, where we can actually calculate a rate based on this. And so again, if we were measuring concentration here across different time frames, we can see that our concentration basically gets cut in half at all of these time points. You'll notice then that the overall change in H2O2 is less and less each time across the same span of time, and so that means that our rate of decomposition is going to go down and down, meaning our rate of decomposition is going to be slower and slower, right? And essentially that's what I just said, that as our concentration decreases, our rate will get slower and slower. And we can actually calculate different kinds of rates. So we could calculate an average rate here. If we were looking at this reaction over 24 hours, we could take all of our rates here and we could average them. That would be an average rate of decomposition. In this case, probably not the best way to describe this, because we can see that our rate changes by a factor of 8 over the course of our first data points to our last. And so that's probably not the most accurate way to describe the rate of this chemical reaction. Oftentimes in chemistry, we're going to measure an instantaneous rate. So if we mix two things together, we often, if we measure the rate as quickly as we can when we mix them, that can be generally a pretty accurate way to understand the rate of a chemical reaction. And that would actually be the initial rate. the instantaneous rate is going to be if we essentially look at just 2 data points and figure that out. So an instantaneous rate would be what is essentially shown here, where we have some change in time over some change in some concentration over some change in time, giving us an instantaneous rate. And it may help to think of this in terms of a graph. And so, for example, our initial rate will be here, where we take our first data point, and then whenever we measure our first time point, we get a change in concentration over a change in time. That would be our instantaneous, or our initial rate. If I can keep those 2 I words straight, this is our initial rate. And then this could be an instantaneous rate. And then, of course, if we averaged them, we would have an average rate. Okay? So we can generalize this as well. And we, of course, want to take into account different stoichiometry for a reaction. And so say we have some generic reaction where we have A going to B, and our lowercase a and our lowercase b here are representative of our stoichiometry of our reaction. So we would say that -1 over A multiplied by the change in the concentration of A over the change in time is equal to basically the positive version of that for B. And so if we were to apply that to an actual chemical reaction, say we have 2 NH3 going to N2 and 3 H2, what would our rate expression look like? And so if you want to take a moment to think about that, write it out maybe, that could be good. But I will show it here, where our rate is going to be equal to -1/2. Again, we get that 1/2 from this 2 in front of the NH3, multiplied by the change in concentration of ammonia over some change in time. That'll be equal to our products, because we just have a 1 with N2. This would be just 1 over 1 for our stoichiometry, so we just leave that out. Our change in concentration of N2 over time, change in time, and then 1 over 3 for H2. Something I'd like to point out here is that because H2 we're going to produce 3 moles of H2 for every 2 moles, or let's think of it relative to N2, we're going to produce 3 moles of H2 for every mole of N2 we produce. We need a 1/3 present in order to basically make those rates even, okay? And so if we think about this again graphically, we have our product here, our NH3, that's going to be decreasing, and then our slope for our change in H2 is going to be approximately 3 times the size of our slope for our concentration in N2, which is just based on our stoichiometry there. And if you multiplied this 9.7 times 10 to the -7th by 3, you would get approximately this 2.9 times 10 to the -6th, which is about a factor of 3 difference there. Okay, so that's it for our intro to kinetics. If you do have any questions, please let me know. Otherwise, I will see you in class, and I hope you have a great day.